In this video, we're going to start to talk about pressure measurements. Okay, now pressure measurements are all the way through air conditioning and refrigeration, as well as gas and oil. We deal with pressure in every aspect of air conditioning or HVAC. So what I really want to do is limit this pressure measurements to air pressures. Okay, so why do we need to measure? We need to make sure all combustion appliances vent properly. All HVAC systems are installed according to manufacturer specifications. Buildings and their related HVAC systems produce comfort, and buildings and HVAC systems are efficient. Okay, so the object is we need to know exactly what's happening inside that environment, inside the comfort environment or the conditioned space, depending on how you want to refer to it. And the only way to make sure is to measure. Okay, we know that building and HVAC systems are durable. We know that buildings and HVAC systems do affect IAQ. Okay, we want to make sure that they don't. Okay, so it's possible for building an HVAC system to have real effect on IAQ, and that's why I want to explain this statement a little bit. But we don't want them to. Okay, we want everything to be a positive environment. We don't want any negative effects. Okay, we have common duct problems that when you look at this building, you can actually take a look at this and see the common duct problems. Starting from the top, this air handler up here, we have leakage out of the supply ducts. Okay, those are the red arrows. Our ductwork is leaking. We're pulling air into the system through leaking return ducts. Well, obviously that's a problem because the attic air is not the cleanest in the world. It's also an energy efficiency problem. Okay, same thing in the basement. If I have duct leakage all over the basement, okay, I'm going to be pushing the air into the basement and pressurizing this area. But if I have return duct leakage, okay, I could be pulling the gases from the water heater and any other fuel burning appliance into the return air and pushing it out throughout the house. So duct leakage is a pretty major problem. And this is by far the biggest problem we have to deal with and things we have to look at when we're designing and installing air conditioning systems. Over the recent years, more problems do exist. We have tighter homes. We have more exhaust fans. We have more combustion equipment, both wood and gas. We have more zones in a house. By zones, I mean different areas of comfort, more thermostats, more units. We have larger and more multi-story homes. There's also additional societal trends. Okay, it's all about comfort, all about me. Okay, we also have increased competition among HVAC contractors for businesses. We have increased third parties looking at efficiencies. We have higher homeowner expectations of comfort. We also, this is none listed here, we have a lot of insurance claims, so I can guarantee the insurance companies are going to be looking at the hows and whys of things that were installed. Okay, we also have more homes with forced air heating systems, more attached garages. Every one of these reasons can affect pressure in a building. Anything that can affect pressure can affect IAQ. This is an example of a ductwork, a system in an attic. Okay, how many problems can you find just looking across here? Okay, I see things like return ducts that are not pulled straight. I see tape coming off. I see insulation on that bottom piece of ductwork. I see a crushed piece of supply of flex duct. Okay, I see possibly another crushed piece of flex duct back right to the right of that the joist that's up and down. Okay, I see some connections, if you look closely back here, that are not taped or masticed. So this system is leaking badly. Tightness of houses is being increased for energy efficiency. Tightness increases pressure differences within a building. In other words, I could have a basement in negative pressure, attic or second floor in a positive pressure, or vice versa. And all of these issues are going to cause problems. Okay, what we hope happens in an environment, in our perfect environment, all of our vents draft in the correct direction. We pull in controlled outside air, and we have our vents all drafting out. Kitchen exhaust fans fireplace vents, everything else is drafting in the correct direction. Backdrafting is why we care about tightness and pressures in a house. The key to understanding backdrafting is understanding the driving forces that create negative pressures. Okay, this is an example of backdrafting. If I have a negative pressure that's created by that stove exhaust fan, all of a sudden this house has more exhaust than it has intake. So backdrafting happens when the air actually gets pulled down the exhaust pipes and comes into the house through the vents. That's backdrafting. So again, this diagram, we got to make sure we bring in fresh air through our whole combustion process. And we got to make sure we have enough air to overcome our exhausts. So this is the inside of, let's say, a gas furnace. Okay, I know it's not the best process, but again, we have our combustion side, which comes across the darker black arrows. Okay, and then we have our air side, which blows across. Okay, so this is our heat exchanger. The combustion and the air will never match. And again, that's very important. The combustion air, which is in the black arrows, will never come in contact with the circulated air, the return from the house and the supply to the house. This could be air conditioner as well. It doesn't matter. Okay, but again, we need to maintain two separate systems. Backdrafting is the biggest problem we have with building pressures. The backdrafting causes that air to flow backwards in the furnace. Now, you can always tell the backdrafting, just as a hint, while you'll go over it again when we talk about gas furnaces in the future, but you'll always see rust. If you see rust around the combustion area of a furnace, there has been backdrafting happening because the flue gases are flowing the wrong direction. So let's get back to what we're talking about with pressure. Textbooks define pressure as a force pressing against a surface as stated in weight per unit area. The force acts as a right angle to the surface uniformly in all directions. Okay, air pressure is the measurement of molecular density. The greater the density, the greater the pressure. When molecules get pushed together, the pressure increases. When they get pulled apart, the pressure decreases. So again, we have weight, which is force, and it's being pushed down into this bucket of water, and then we have the area. So pressure works at right angles. Okay, so my pressure is down here. Pressure could also be outwards at right angles, from left to right. It doesn't matter what direction, but pressure always works at right angles. So normal air pressure at sea level is 14.7 psi. I guarantee you need to know that. In Denver, Colorado, the pressure is 12.1 psi. At 35,000 feet above sea level, the pressure is about 3.4 pounds per square inch. So what is pressure? When air is warmed in the combustion process, the molecules become spaced further apart. This also happens with sunlight or any time you heat air. The molecules move further apart. The density decreases and the air rises. This is known as stack effect. Okay, when air rises, it's warm. When warm air rises, cool air replaces it at the bottom to be warmed. Okay, this is called stack effect. Pressure will always move from a positive to a low pressure unless you're pushing it with a fan. Okay, so again, pressure will always move from an area of higher pressure to an area of lower pressure unless you are pushing it with a fan. Pressure is measured most often in the HVAC industry, and again, I'm talking building and duct pressures, okay, in inches of water column. It's WC. Okay, several tools are available to measure these pressures. The first one, and probably the oldest one, is a U-tube manometer. It's filled with water and it measures how far the pressure pushes the water in 1 inch. This is where the 1-inch water column comes from. Okay, this circle here is a beach ball. Okay, you take a U-tube manometer connected to the beach ball, that pressure will push up, and there's a gauge on the side of this U-tube that tells you it's basically inches. It's a ruler. Okay, pushes up the water 1 inch. It is by far the most accurate way of measuring, as long as you use clear water or clean water. It has a little dye in it, but it doesn't change the density of the water. Okay, it still is by far the best way to measure in terms of accuracy. There's a lot of electronic tools out there, which we'll talk about, but the water column. Now, an incline manometer is a more refined version of the U-tube. It measures the smaller pressure, more common to air handlers and homes. It has a maximum of 249 pascals, which is 1-inch water column. See, I've just given you a formula there, or a conversion. 249 pascals equals 1-inch water column. Most of the pressures you're going to deal with is in inches of water column or fractions of inches of water column. Unless you are a building designer or really doing an investigation of what's going on in a house, you're not going to use an incline manometer, and you're probably not going to use pascals. Then we have the gauge manometers. The gauge manometers came next in the step of this whole thing. They eliminate the use of liquids, and they use gauges to do the same work. It uses a high and low pressure tap. Okay, so you put your static pressure probe in a piece of ductwork facing the airflow, and your gauge will show you what the pressure is in that ductwork. Then finally is basically what we're using now. Digital manometers. Digital manometers are available. They eliminate all mechanical parts, and it's all done with circuit boards and sensors. Okay, I regularly show off my Testo smart probes because it's a digital manometer that actually connects to my phone or iPad for tracking purposes. I can see exactly what's going on over a period of time, or just right there. Okay, so the digital manometers have also evolved to be just sensor probes. Now, we can install digital manometer and that type of technology in ductwork and use it with building controls. And we'll talk more about that as we talk about our design terms. The basis of all pressure measurements is to compare the pressure in one zone with another. For example, we want to compare the pressure on the inside of the building to the outside, from the inside of the duct to the inside of the building. For the HVAC industry, fans and blowers are usually used to move air. The movement and force provides a positive and a negative pressure around the blower. Blower assemblies are constructed to pull air through the return ducts, filter, and then push air around a heat exchanger or coil and through supply ducts. They require careful adjustment to produce enough volume and velocity to maintain comfort at design conditions. Let me repeat that. They require careful adjustment to produce enough volume and velocity to maintain comfort at design conditions. Volume is measured in cubic feet per minute, or CFM. Velocity is measured in feet per minute, FPM. You have to have both in order to maintain comfort at design conditions. There are two types of blower assemblies available. One is direct drive, one is belt drive. Direct drive runs about 1050 RPM on high speed. It's supported by a motor shaft, and if you have variable speed direct drive, it requires a multi-speed motor. They're mainly used in residential applications, even though they're starting to make it into the smaller commercial applications as motor technology improves. Belt drive, the motor's usually around 1725 RPM. The blower wheel is supported by the shaft and bearings, and the variable speed is obtained by varying the setting of a split pulley. You're going to see these used in the light commercial and heavy commercial applications. You rarely see these in residential unless it's very old equipment. So again, you have direct drive and belt drive. Blower assemblies okay, are mounted in the bottom of the or side of the air handler. Don't worry about anything else on here in terms of temperature rise and stuff like that. We'll talk about that in the future. Right now, I'm more worried about this is a direct drive blower. The return air pulls into it. Supply air pushes out. Now, this is an extremely important picture, and we're going to, in our next video, which is Pressures 2, we're going to talk more about this. But return air, because it's being sucked in, is a negative pressure. Anything past the blower, which is our point of pressure change, becomes a positive pressure because it's being pushed out. So return is always negative, supply is always positive. Again, don't worry about the temperature stuff on this. I'm just using the picture because of that blower. It's important that the drive on the motor and the pulley on the blower wheel, when you're dealing with belt drive blowers, be perfectly aligned. Any belt wear more than normal is most often attributed to improper alignment of the pulley and motor. When we put a blower in a furnace, the supply side, as I just showed you, is a positive pressure. These are fan pressures you see referred to. The return side of the fan, the sucking inside of the fan, is a negative pressure. So we have two pressures, and the point of pressure change is the fan or the blower. Okay, so again, return side is negative, supply side is positive. Doesn't matter what type of air conditioning I'm doing, what type of ventilation I'm doing, this is always true. Fan and system pressures can always be found on the furnace nameplate, also called a data plate or rating plate. If you're taking a certification test, there is a question on there that says, where do you find the system pressures? It's on the furnace nameplate, data plate, or rated plate. Most often, these are called, it's going to be listed as total external static pressure or external pressure. Okay, but it's the total external static pressure. That means a lot in HVAC for such a short phrase. Tune in for the Pressure 2 video, and we're going to talk more about how we deal with these pressures when we're talking ductwork evaluation and design.